Okay, so today, topic 38, we move on from time series data to time series models. So here I've listed a bunch of time series models, and I will tell you all that within our curriculum, excluding the appendix, it actually ends at Arima here. So we're actually going to cover all of these today. These are what we're going to talk about today. In your phase 4, actually, let me just pull it up real quick. In phase 4, I really do recommend going through the appendix, especially for time series and natural language processing. So for this week's stuff and next week's stuff, highly, highly recommend the appendix, just because it really takes your project it really takes your project to the next level. So for time series, the appendix brings you through Arima models, and I'll talk about what Arima is later, and also Facebook profit. Now, Facebook profit, I'm not going to talk about specifically today, but Facebook profit is basically very, very similar to all of these models that we're going to talk about today, but Facebook kind of added their own little twist to it, and it is a little bit more automated. This lab basically walks you through how to implement it. It's good to compare your results between Facebook profit and the models that I'm going to talk about today. But just know that for phase 4, you're not expected to implement anything that isn't part of the core part of the curriculum. So even though I'm recommending that you go through the appendix, these are kind of like nice to haves for the project, but really not necessary. So don't need to get too stressed about that. And since we're here, because we're doing NLP next week, natural language processing, for NLP, deep NLP is pretty neat. I would say like the first half more so than the second half, because that gets very abstract, but just in case anyone's looking for it at NLP, I know Amir, you're looking at NLP. Kind of like this first half is probably more relevant to the projects that we will be working on as data scientists. I'll give more context on NLP next week. But yeah, just wanted to make that note. It's really just 2 labs, and they're not very long either. So I do recommend that you look at them, although not a requirement. Cool. So time series models, as you can see here, I've listed 8. 8? Yeah, I've listed 8 over here. This article that I've linked over here actually has 11. And I'll sort of talk about why it isn't as intense as it looks. So we're not going to talk about any of these. I actually myself haven't really had to use any of these, so I haven't had much experience with these others as well. But the way that these models are work and why I say that they're modular is because the letters in each model define what components are being used as part of building these models. So any model that follows this form or has like ARIMA or S's or X's, these are all traditional time series models. And we're going to see in a little bit, these are all linear models, very, very similar to how linear regression is structured, but time series instead of regression. And I'll talk about those differences later as well. But basically, why I say that they're modular, first we have AR models. So AR models take into account autoregression. And if you remember, autoregression kind of makes use of actually both AR and MA both use our ACF and PACF, but we'll get to that later. So anytime you see AR is when you have autoregression as terms in your model. If you have MA, means you have moving average terms. ARMA is a combination of autoregression and moving average terms. Then you can bring in differencing as well. And this is where the nuance about, when do you do differencing? Do you put differencing on your model first? Do you on your data first or not? We'll get into that later as well. So there's differencing. The most common one is actually Arima models that take into account all 3: autoregression, differencing, and moving average. The I, for some reason, stands for differencing. And then other ones that we have, if we include an S stands for seasonal. That's why this is important, because if you want to take into account seasonality, it would be with a Arima model or any of the models that have a letter S in it. You have Arimax. So the X stands for exogenous variable. So far we're talking about single variable univariate time series data. But if you wanted to include other variables, very similar to how you would for linear regression, I'll talk about that later as well. It would be when any of the models have an X in it. And then if you want to put them all together, you have Saramax models. And I'll actually talk about Saramax at the end, because there's something like a grid search for AutoArima. I'll talk about that later. not to confuse you all. So because of that, it's all very modular. And these models all follow a very, very similar structure as linear regression. And like from this version over here, we're going to get into the weeds of this later, but you can see that there's like a y, there's like a yt minus 1, there's like a coefficient here, and there's some like intercept looking thing. So they all have a linear model. They are all linear models. The letters just define how the data looks, what kind of data you're adding, and what kind of features you're using in your model. The library that we will be using for these models is also stats models. So not scikit-learn, but the same library that gave you that, nice table tabular output for linear regression. So that's familiar. Okay, so let's go step by step and let's put these components together one by one. So first we have AR models. So you can do an autoregressive time series model, and autoregression basically makes the assumption that observations at previous time steps are useful to predict the value at the next time step. It is one of the simplest time series models in which we use a linear model to predict the value at the present time using the value at the previous time. So intuitively, this sounds like it would make sense. So let's just say we have a time series that is moving fairly stable, maybe with a little bit of up and down. You can say that the prediction for tomorrow's price is equivalent to yesterday's or today's price, because I said tomorrow, today's price multiplied by some coefficient plus some constant term. So that is what AR model is. That's what an AR model is using as a feature, basically prior time steps, like values at prior time steps to build this model. So this is a representation of an AR1 model. So the numeral 1 denotes that the next instance is solely dependent on the previous instance. So this phi or phi, some people call it phi, but I'm going to call it phi, is a coefficient which we seek so as to minimize the error function. So the way that these linear models optimize, especially within stats models, is exactly the same way that our linear regression models optimize the stats models. I talked about that last phase, where stats models actually uses linear algebra to solve for their coefficients. That's exactly what's going on here as well. So with AR models, the order of AR is the number of lag terms that we're using to predict the present value. AR1 only uses 1 lag, AR2 uses 2 lags. So instead of this, they'll actually scale up, and let me just write it out so it's clearer. So you'll see another term plus, and then you'll have a phi 2 multiplied by yt minus 2. So if you have an AR2 model, it means that the prior 2 time steps are important in coming up with the prediction for the next time step. So this phi is what we're trying to figure out the optimal values for in the way that the algorithm optimizes itself. Okay, so this, you can add as many AR terms as you want. So one of these is considered an AR term. You can add as many as you want, or as many as your EDA suggests that you add. So how do you do that? Let me just clear this for now. You use your ACF and PACF graphs. So how do I know whether I want to start with the AR1, AR2, AR3 model? You look at our ACF and PACF. So we know that, and this is a really great article that I really recommend reading through to understand ACF and PACF. But what to be honest, still mix up which one to look at for which term, because ACF and PACF, one of them tells you what to do for AR terms, one of them tells you what to do for MA terms. So I wrote it out here. If your ACF is gradual and PACF drops off, look at autoregression. And if PACF is gradual and ACF drops off, you want to look at moving average, which is coming up next. If it's unclear, you can actually try out a bunch of different combinations of AR terms and MA terms. And that is in AutoArima. And I'm going to talk about AutoArima later, because that's sort of like grid search, like trying, all right, maybe I want to try the range of like 1 to 5 AR terms, as well as 1 to 5 MA terms to figure out which actually fits my data best. Any questions at this point? Cool. I'm going to open up this AutoArima because I want to talk about it later. All right, so if we see something like this, where ACF is gradual and PACF drops off, usually you want to use an autoregressive model. So this is actually very similar to what we saw yesterday I think yesterday with our shampoo data, where is my PACF graph? Oh, did I not have my PACF graph here? All right, let me pull it up real quick. I know I got it here. All right, so this was our ACF and PACF graphs from yesterday. We saw that ACF was gradual and PACF was a lot more, it drops off and is a lot more jaggedy. I don't know, I forget the scientific word for that. But basically with this, we can see that, and we did take note of this, that there are 2 significant lags for each of these ACF and PACF graphs. So because of that, we want to start by doing an AR2 model for this data. But let's just try one first. Okay, so how do you use an AR model? Actually, any of these models will work. Within stats models, and I'll talk about train test in a bit. Within stats models, you can actually get Arima models, AR, MA, Arima, RMX. You can get all sorts of combinations. My preference, and I think it'll just make it easier for you to test as well, is for anything that needs AR, MA, or differencing, just do Arima, because you can set the rest of the parameters to be zeros, and it just makes it easier to test. So you're not importing a bunch of different kinds of models. But that's my personal preference. If you want to use pure AR models, instead you can see I'm using Arima here with 100. I'll talk about that in a bit too. It doesn't matter. You'll actually get the exact same results whether you use Arima model with 100 versus an AR1 model. Okay. So before we start modeling, let's talk about train test fit. For time series, because it's always forward looking, we have to be a lot more, what's the word? We treat our train test different because we're always forecasting. It makes sense to not randomize our data because the sequential nature does matter. Instead, what we usually do is we segment it at some point. Whether you do 80-20 split, or actually where you choose your split actually does affect your model's performance quite a good bit. So for example, here I decide to split at 24 because I know that this is a 3-year shampoo sales. Let's just say I'm taking my train set to be the first 2 years, test set to be this last year. And you can see that why there could potentially be issues is in the data itself. We can see that it looks like the trends are kind of different between my train and my test set. And this is something that in your projects you can definitely look out for as well to figure out, okay, let's say my train and test happens to be split where there's like a financial crisis. Then obviously what your model is being trained on will probably not apply to your test set. And for that, you can actually choose for time series data to move your split a little bit further back so that it can take into account as much information as possible. Another thing that you can do for time series models with regards to train test split is, because over time, the things that have happened more in the past matter less. So what you could do is after figuring out your best models, you can kind of refit your models with the best parameters using your entire data set, not just your train set. So those are different things that you can definitely talk about in your project. When we get to the project weeks, I'll get into more detail with this, but things to think about for now. Questions about any of this? Okay, so for all of these models that we're going to talk about today, I'm just going to use the Arima model object. To use Arima, the syntax is slightly different. So first, I instantiate my Arima, but when I instantiate it, I actually instantiate it with the data. So this is the train data. And by the way, train and tests, I'm splitting it at 24 over here. This order, the order of your order really does matter. So it's always P, D, and Q. I don't know why the letters they chose are P, D, and Q, but P is autoregressive, D makes sense, is for differences, and Q is for moving average. So you can see later when we start to incorporate MA and differencing, we'll just change up these numbers. And when you instantiate it, you can just do a dot fit. So really another small nuance about making predictions with time series data, there is a difference between prediction and forecasting. I did talk about this a bit yesterday, but in terms of the methods used, predicting and forecasting are different. So for your train set, you actually use a dot predict, and for your test set, we're forecasting 12 steps ahead. And there are actually a few different ways to do forecasts. This method of forecasting actually does not take into account any of the test sets data. I'll send out an article that walks through the different ways to make forecasts. So I'll get into this once we look at the results. So once this is done, we have our summary table. And the summary table is the same as the summary tables that we have for linear regressions. That's very, very convenient for us. Let me make sure everything is run real quick. Okay, so we have this summary table over here. The way that you interpret a lot of this is very, very similar to with linear regression. Although there is no R squared, so instead of R squared, the equivalent of R squared is AIC score. So AIC score and actually BIC, but AIC and BIC are usually correlated or related to each other. So usually you just want to look at your AIC score. And at this point, AIC of 278.951 does not mean anything. However, for future models, you want to compare AIC scores and you want your AIC score to be lower. So the lower, the better. So your first model is usually some sort of benchmark baseline. There is no goal best AIC. AIC can also go negative, and the negative AICs are actually even better. So in terms of choosing best model, in terms of model fit, you want to look at AIC. Okay, so let's go down to this table over here. So there's a constant, there is a AR term for lag 1, and then there's this sigma error. So the sigma error you don't really have to worry about too much. But the main thing you want to look at is this coefficient over here, and is it significant or not? So if you remember from linear regression, we want all of our variables to be below 0.5. So in this case, we can actually see that this AR term of 1 is not significant. And we only have this one term that holds any information. So this model, not very good. I mean, as expected, we saw that 2 terms are significant, but here we're only using 1 for this data set just to test it out. So over here, if you remember, we did dot predict for our train predictions, and to test predictions, forecast 12. I actually plotted this on a graph as well. Make sure this is run. So this is our original data, and these are our predictions. Now our predictions don't really seem like they match our data very well. For the train set, it's really because they're only taking into account the step right before it. So 1, there's a lot of lag, and 2, it's not able to capture as much fluctuation because there's only 1 term and you have to multiply it by a constant number. How are you going to get these predictions? So it doesn't fit it very well. Next, for the test predictions, you see that this is a flat line. And for using this forecast function, it is to be expected because in this model, you are making predictions based on the price of the day before. Now, at day 24 or day 25, the train set knows your model knows up till day 24. So you can make a prediction for day 25. However, for day 26, your model has no more information because it does not take into account the price of day 25 from your test data. So therefore, for any AR model using dot forecast, your forecast will plateau out and just become a straight line. As I talked about with regression as well, model fit is one thing. So AIC is one thing, but it's important to look at the predictability or the predictive power of your model. So just so that we can compare, let's take a look at our RMSE. So right now, I'm just looking at this mean squared error between my predictions and my actual values. As expected, my train RMSE is about 71, and my test RMSE is 269, so almost 270. So not very good. You can see that there's severe overfitting, and we'll see how our future models will do any better. So in your modeling process, every time you run a model, things I would like to see are an output like this, as well as RMSE scores. Any questions before we move on to more models? Cool, and also label your graphs. I did not label this here. All right, so let's take a look at an AR2 model, which we do expect to perform a little bit better because of the PACF and ACF EDA that we did. So looking at this, all I'm changing is I'm changing this to 2 from a 1, and all of the code is the same. So already we can see that, all right, we have at least one significant term. This term is insignificant. For time series, it's not that easy to just drop insignificant terms. So this is actually something that we just have to make do with or try other models. And we look at the AIC score. Here we had 275, a little bit better. So we actually cannot just simply drop this. And the thing that you would have to do is just do other models. But sometimes if this is your best model, you would actually still just stick with this. So let's take a look at what this prediction looks like and our errors. So our train RMSE and test RMSE have both gone down a little bit. You can see that now with more terms just means that your predictions are able to fit your training data a little bit better. So because of that, we expect to see lower RMSE, and for the test, we're doing a little bit better. And you can see that predictions are more varied, a little bit more after the 24 mark versus when we only have one lag term. That's because it has more information to propagate down, but eventually it also flattens out. Any questions about this? All right, so it turns out that I guess using just the prior 1 to 2 days of data, not enough. What is something else that we can use? Let's look at moving average models, or MA terms. So sometimes a past value is not a useful indicator of what will come next. Consider a system that is subject to a lot of shocks and volatility. If a previous time period experiences a shock, it may cause an error for future predictions if we just use that value. So a moving average model actually does help to address that behavior. So moving average term in a time series model is a past error multiplied by a coefficient. So you can see that this actually looks very similar to what we had before. But instead, what we have here is we just have an average as our constant. We have some error value here. And then what we have is a constant here multiplied by our past error. So what we're taking into account here is what was the error at the prior time step, and we're going to adjust this coefficient accordingly. Questions about this? All right, since these models are modular, we can also talk about differencing real quick. So we talked about what differencing does. Differencing helps your data to achieve stationarity, because stationarity is one of the assumptions for using any of these linear time series models. So we know what differencing is from yesterday, but just to recap, difference value is equal to the present value minus the value at the next lag. So a time series which needs to be difference to be made stationary is said to be an integrated time series. So that's just, I guess that's where that's where the I comes from. It's integrated. So remember, this is our original data. This is it with one difference, which if you remember from yesterday, one differencing is actually stationary enough, but this is two differencing. It's overall like a little flatter, you can argue. So now that we've talked about including past errors, as well as including differencing, we can put that all together in an Arima model. So from that, I mentioned that, oh, by the way, for an Arima model, everything is just additive. So here you can see in an Arima model, we have our, these are our AR terms, and then these are our MA terms. And the differencing is basically incorporated into the Y. So it's really difficult, as I mentioned yesterday, to undifference your data. So if you're using Arima out of stats models, it'll actually do all of that for you. So you don't have to worry about that. And what that means is you actually feed in your raw data in, you feed in your undifferenced data into the model. So let's look at this. These are the same from yesterday. We've pretty much decided that 2 lags is something that we will explore. And so let's fit this. Let's fit with 211 for now. So we're going to fit 2 AR terms. Let's do 2 MA terms, see what it's like. And then we're going to call .fit, and we're going to make predictions the same way. Cool. So here you can see that, all right, we have some insignificance, actually a good bit of insignificance, but let's just see how our model does. The AIC is at 265. And if we compare that, I think we had 270 or 268 before, 275. So it's fitting a little bit better. That is good. And then from here, we'll take a look at our predictions. So our predictions are an array. And if we look at that, this is what our train and test data looks like. Looks a little bit weird because in the training set, it's actually trying to figure out what the best coefficients are. But you can see that our test RMSE is doing a little bit better. So that's good. So here we have a train RMSE that's actually worse than our test of 233. Our test RMSE is down to 165. So overall, our test RMSE is better than all of the prior models that we have done so far. Cool. In terms of implementation, I mentioned that with your EDA, figuring out the two lags is to be used as a starting point for your modeling. So you can see here, still not optimal results, right? Our data, our lines are not really fitting as we would like them to. So what you can do is, even though two lag terms, like using two, where did I instantiate my Arima? Using my 212 is what I figured out from doing EDA. Doing additional differencing or including additional terms might help more. So what you can do is implement what is called AutoArima, which I have over here. And AutoArima, actually, this is not a great thing to pull up. AutoArima, I have a walkthrough here. AutoArima is something that you do is very, very similar to grid search. And AutoArima is something where you can actually give it values of starting P, starting D, starting Q, maximum PDQ. And it's just going to run a bunch of different combinations of PDQ values to give you your optimal model. And it can spit out your AIC score as well. So when you're doing your EDA and you get your starting values of PDQ, definitely use it as some sort of baseline first, but you can definitely adjust. Those like two lags are not rigid. You can definitely add more lag terms, maybe remove lag terms, and then see what works out the best using AutoArima. I believe, let me see if I have this. I don't think I have it linked anywhere. I'll send it over to the channel so that you all have it. Cool. Any questions about, oh, here's where I am. Any questions about Arima models at this point?
So the AutoArima is the grid search equivalent of the other models? Okay.
Yeah, AutoArima is a grid search equivalent. What's cool is, I don't know if that's considered cool or not, but if you're running AutoArima, it's actually running a bunch of Saramax models. So again, Saramax is an inclusion of seasonality as well as exogenous variables. So if you just set everything else to be 0, it's the same as a regular Arima model. You might see something that looks like this in your output too. And this basically brings back that the way that this particular algorithm optimizes is through linear algebra methods. So if you're seeing something like this, near non-invertible roots for order, blah, 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 it means that with that specific combination of terms, linear algebra cannot solve it. And using this library, you could pretty much just strike out that combination.
Gotcha. Thank you.
You're welcome. Anything else? All right. So main thing to pick up from here is that these traditional time series models are linear models, and they're basically using past time period values and past time period errors as features in making predictions. And that's actually really, really, I felt that was pretty smart. But also a lot of these linear assumptions do hold and do affect the model. So for example, if you know that 3 lags ahead, your linearity assumption, let's say the time series itself, and then lag it 3 times, you plot a scatter plot, not very linearly related, you actually won't have that term doing very well. So a lot of the concepts do carry over, although it's not the most important thing when dealing with time series models, unfortunately. Okay, on that note, do I talk about, yeah. So on that note, exogenous variables, because this is very, very similar to linear regression. If you want to include exogenous variables, when you add an exogenous variable, it's just going to show up in this table over here, just like your linear regression. And with your exogenous variables, because those are additional features, not the time series itself, you can pretty much play with those features the same way you play with them with regression. So if there's a high p-value, don't use it. If you have a low p-value, you can actually learn about the relationship between exogenous variable and the time series the same way that you would for a regular linear regression. And if you're implementing exogenous variables, I believe you just have to give like your X values there as well. All right. So dealing with exogenous variables, things to consider, the direction of causality is very, very important to consider. I know last phase we talked about a few people having, or some of your projects we talked about you all having confounding variables where you're trying to predict something using something that is a result of that prediction. Like for example, if I wanted to predict, I don't know, if I wanted to predict whether it will flood or not, maybe one of my features is like, is there extremely heavy rain? Actually, no, that's kind of like, that is kind of correct causality. Or let's say you want to predict how many points scored in a game, and one of your variables you're using to predict is whether you end up winning or losing. So the direction of causality is very important to consider, because if you're doing something that's reverse causality, it doesn't make sense to add in your model. It might still be mathematically significant, but doesn't make sense to include in your model. Exogenous variables also need to be different at the same order as your endogenous variable. Now, this effect of differencing, as you saw for here, which I didn't really point it out, but for here, I was still feeding in my same train set. Even though it's being different, when I output my predictions, it is also still undifferenced. So from that, you don't have to worry. You don't have to worry about differencing your data. So even though it needs to be different at the same order, that's usually not something that you have to like look into and consider. Cool. And finally, there's Ceramax. So with Ceramax, if you see that there is seasonality in your data, you can include seasonality as part of your model. And the way that you include seasonality is you have to tell it your period. So here, this is a Ceramax model and how you instantiate it. You have seasonal PDQ, and let's say it's monthly data and you have a yearly season. Then you have 12 periods in the season, you tell it 12. Here's also how you would give the exogenous variables. Exogenous equals, you feed it like your array or your data frame, that'll work too. And then, yeah. Cool, so that's all the time series models. They're very, very modular. Usually the most commonly used ones are Arima because of AutoArima, and also because ARI and MA are the main components of time series models. And if you have any of these additional components that you want to add, you usually just jump straight to Ceramax versus like Arima or Arimax. Cool. And oh, nice, I have all of this here. So I have Ceramax over here, seasonal decomposition. This is what I talked about yesterday. And then we have this modeling cheat sheet. This is the one that I have above, AutoArima, and a Ceramax walkthrough of a project in case you ever wanted to implement Ceramax in your Cool. Any questions at this point regarding the models before I start talking about like project expectations?
Can you just clarify one thing? The 212 or the 210, just to I forget like which what each represents.
Yes. So I know the ordering is a little weird, but P is AR terms, the number of differencing or order of differencing, and then Q is number of moving average terms.
Okay. All right. Thank you.
You're welcome. Yeah, PDQ is something that'll start to stick. All right, anything else? Okay, so for this time series project I mentioned yesterday, the data set you're given is roughly 200 zip codes with monthly median average housing prices that goes back, I think, around 10 plus years. And the idea is to make forecasts and suggest some zip codes to invest in, or to figure out what the best zip codes are to invest in. Several ways that I suggest going about this project. One is you can do the project as is, maybe automate a process to do a bunch of time series models for like maybe, yeah, automate a process to pick best PDQs and spit out forecasts. That's one way that you can do it. That style of project is going to be very focused on the automation process. But I still do want to see some EDA done on 1 or 2 zip codes, just so that I know that you're aware how all of that is done. Another way to do it, which actually most people end up doing, is start by shortlisting zip codes at the start. And the way that you shortlist is up to you and up to your business case. So let's say maybe you just want to look at the zip codes around where you live. You can do that as well. Or let's say you want to use some sort of calculation to figure out what are the zip codes to shortlist. Maybe you want to look at, I don't know, population growth, things like that. You can do that as well. So in terms of approaches to this project, I would say pick one of those two. Now, when you shortlist, I would say shortlist to about 5 to 8 zip codes. That's a good number to do like a good amount of analysis on each zip code. Any questions about that? All right.
I don't know if it matters, but do you know what the area is of the
data set?
Yeah.
I think they have zip codes spanning all over. I think it's all over the US because I've seen California, I've seen New York for sure. I've seen that they also have like, they definitely have North Carolina, Virginia. I don't know what the parameters were for picking the zip codes that are in the data set, but they're kind of like all over.
All right, thank you.
Yeah, so you can kind of arbitrarily pick, or at the very start of your notebook, if you decide to do an approach like that, just tell me why you're deciding to pick several zip codes. Maybe you're doing that based on areas that you are familiar with, or maybe you're doing it based on like highest income or something like that.
Oh, so we could pick like a region and then you find like sort of a specific, you know.
Yep.
If they meet a specific criteria, pick that.
Yep, as long as you can justify that it makes sense in your business case, you can do that.
All right, thank you.
You're welcome. Cool. Now, if you don't decide to use the data set, and also the data set does cut off at I think like 2019, I think. So if you want, the data set is from Zillow and you can actually find more recent data if you'd like. But if you want to do a completely different time series analysis that isn't on housing prices, you just need to look for a time series. And I do recommend trying to have at least 300 or so data points in your data set in order to do an effective time series analysis. So if you find a data set and if you don't want to do the provided data set, just send it over to me so I can approve it first. Don't work on it before I approve it just in case. And then you can go from there. Cool. So it can be anything. Like I've had people do it on like stock prices, on things like, I don't know. Oh, inventory is something that's been done as well. That was pretty common. Sales. This one's on shampoo sales, but this is too small of a data set to do it on. I've seen it on what else? I've seen a lot of housing prices still. But yeah, if you would like to do it on something else, just let me know.
If we research, if we like look up on Kaggle for data sets, should we specify, like, is there like a specification in the search? Like,
ooh, good question. Let's take a look. It's been a while since I've looked at Kaggle data sets for forecasting. So let's find out. So data sets and the tasks, I wonder if they do like forecasting. All right, so forecasting seems to be one that will make sense. Again, do look at the number of rows. So here it looks to be that there are, okay, there's definitely at least like 500. Oh, okay, yeah, it looks to be like 500, 600 different rows. So this would work. If you would like, you could find something that's on like, wait, let me take a look at this real quick. Oh, okay, I don't know what these are. So these are maybe like different items. But yeah, for this project, it only needs to be univariate. You don't have to include exogenous variables. You just need to have one column of data that has enough rows, and then you should be good to go. But do send me your data in case, just so I can prove it first.
thank you.
You're welcome. Anything else at this point? All right. Oh, yeah, Amir.
Just can you hang back for a second? So a quick question. That's
Oh.
something else.
All right, all good. We can talk after this. All right. So one final thing on with this with your project, again, I want to reiterate that you really only have to do ARIMA modeling for phase 4. If you want to level up, you can implement seasonality. If there's no seasonality, there's no point. Exogenous variables, but if you don't have any exogenous variables, so there's no point as well. You could try Facebook profit as a model. That can be something to implement as well. One more thing to implement is neural networks. So we're only going to get to this in 2-3 weeks, I think. But there is one form of neural network that works for time series data. And it is actually not weirdly, it is actually the same kind of neural network that you use for deep NLP. So I'm going to talk through how these kinds of neural networks work as our last study group. The study group that is on, let's take a look at the calendar. Right, this one, topic 42. I'll talk about the kind of neural network used for time series. So definitely, I think that if you want to do the time series project and you know for sure, good to start early. So that when we get to neural networks, maybe, and again, not necessary, but maybe you can implement a neural network for your time series data. I think that would be cool because neural networks will see much stronger predictions. All right, again, over our 101s, we can definitely start talking about projects, although I know I haven't covered any NLP, any neural networks yet. So I understand that people who want to do those projects are at a bit of a disadvantage, but it's not going to affect anything. Don't worry. But yeah, I think that's all I have for today. Does anyone have any questions? Anything they want to clarify?
Yeah, I had a couple of questions. Could you, for recommendation engines, can you use time series as well, or?
Ooh. So recommendation engines is it's kind of an umbrella term for anything that's making a recommendation. So technically, if you're creating recommendations out of forecast, that is time series recommendation. However, for this recommendation system project, we are focusing on collaborative filtering methods. And I guess I didn't really go very in depth about the kind of data that we're looking for. So let me pull that up since we are here. All right, so the kind of data that we're looking for recommendation engines is rating information or any sort of stars or user to item to rating kind of data. And pretty much your data should come in this form of 3 columns where you have unique users, unique businesses, certain number of, or your associated rating. So this is the kind of data, the provided data set already comes like this. I think it has one additional column of timestamp, which you can drop. So this is the kind of data that you should be looking for phase 4's recommendation system project, because that is kind of the main algorithm that we want you to learn and get familiar with.
All right. And for time series, if we decide to do that, are we expected to show a AR model, a MA model, and then a differencing model? Are we for each type of?
Good question. Yeah. No, not necessary. Especially if you know that, well, you would start with an AR model if your EDA shows that you should start with an AR model, or if your EDA is so inconclusive, then you might start with an AR model as a baseline. But usually, if you go straight to ARIMA modeling, it's usually what people do. Usually, how it works is for each time series, you would start with maybe some arbitrary ARIMA determined by your EDA, or if your EDA is inconclusive, you can just start with random, maybe 111 for ARIMA, and then plug it into AutoArima to let it tell you what the best PDQ values are.
Thank you.
You're welcome. Yeah, we can talk more in detail about the project at 101s, and also when we get to office hours. I think once you start working on the project, the path of which you take your project on will be a little clearer then too. Great. Anything else? All right then. Well, that concludes time series. It's been kind of an intense 2 days. By the way, tomorrow I'm out of office because I'm moving finally. So if you need anything, put it on the channel. I'll still be on there sporadically. But yeah, just in case anyone's trying to reach me, tomorrow I'm out of office. I'll be back on Friday. Cool. Let me stop the recording here.